Thanks, Ben. Welcome everyone to the hackathon, to the LLM hackathon for applications in chemistry and materials. Um, Welcome back to the people that participated last year, and welcome to everybody new. We have so many people participating this year. We're so excited to see what everybody makes. Yeah, I guess I should introduce myself. My name is KJ. I'm one of the hackathon organizers. I'm in Chicago. I work with Ben Blazek at UChicago and Argonne National Lab. And I'm just going to be walking through the Miro board, which if you joined after I posted that in the chat, I'll go ahead and post that again. And then I'll share my screen and we can start going through it. All right, so this is the Miro board. This is going to be sort of our virtual hub during the hackathon. So let's get started over here on this side. So we've got a nice quick start section with links to everything that you'll need. So we have a link to our Slack channel. If you haven't already joined Slack, do that right now. The link is right here. This is how you're going to be communicating with other people in the hackathon. We have the link to our Zoom meeting, which you're all here, except for the people streaming. But if you need this, we have a handy link right here if you want to join later today for other events and speakers. We also have an example of submissions from last year. So if you want to take a look, get inspired, or just kind of see like how people formatted things, that's right here for your reference. And then if you're not familiar with Miro, we also have a nice little getting started with Miro section, so you can use the board well. All right, so moving to the right, we have a schedule of events. So we hosted a teaming event just to get people connected beforehand. That was in April. Today, we've got the hackathon, of course, you're all here, the Zoom link. We have a link to the full agenda. I also put that in the chat of Zoom. So if you need that, just different speakers, we've got different events, things going on throughout the day today. And we have the submission deadline with a link to submission details right here, which I'll go over in a few minutes when we get to that part of the board. So just like a nice reference of links and things you'll need to know. So moving over to the right, we have this pitches and teams section. So if you came to the hackathon with an idea and you're looking for a team, this is the place to be. So what you'll do is you'll select this template, copy and paste it, and fill that in. And then people can select a sticky note and put their name on it and put it on your pitch idea if they're interested. You can also reach out to whoever wrote the pitch on Slack and just get more information to introduce yourself and connect. So this is a great spot for pitches. We also have a time later in the day. So if you have a pitch and you fill out the template here, you can also make 1 or 2 slides. And we have a section for people to give their pitches. So if you're looking for a team or you want to give your pitch to people on Zoom, there'll be an opportunity to do that as well. Cool. So we've got the pitches and team section. If you go down, you'll find this team formation section. In this section, each team has a room, so you can copy and paste this template if you want to make your own room. We have different room tags to communicate with people outside of your team. So we've got like team closed if you have enough members. We have this join up if you're looking for more people. We've got looking for blank, which you can fill in if you're looking for specific skill sets. And we've got taking a break, so you can let people know that you're not ignoring them. You're just not at your computer right now. We also have buttons that you can add for links to important resources for your project. And of course, these like optional add-on fun things. You can make your own avatar. We've got a little instruction box here for how to do that, and like little decorations if you want to make your room a little more unique. I can see a lot of teams already got started. I'll zoom out and see all these different teams down here. You can also zoom in and read about each of the teams and reach out to the team members on Slack if you're interested in the project that they're working on. All right, so back up to the top. This team registration, you can ignore. We maybe went a little overboard on the team stuff. So we decided to get rid of this team registration. We're just going to go by the rooms below as team registration. So going over one more, we've got instructions for how to submit your final project. So the outcome of this hackathon, what you'll need for your for submission is you'll create a video presentation that's 2 minutes or less, just summarizing your team's project. You'll post that video to at least one social media platform. Got examples here: YouTube, Twitter, LinkedIn, Instagram. Just make sure that your video is public so that the judges and other people in the hackathon have access to view it. And then just one team member needs to fill out this Google form to submit your project. Oh, it looks like we've got some people moving stuff around. Let's move that. Oh, someone has it selected, so I can't move it. There we go. Okay, so I'm just gonna move that back down here. Oh gosh. Okay. So yeah, submissions must be received by May 9th at 5 p.m. Central US time. And that's when, after that, the judges will assess each submission. We also have this nice resource library. So if you have some questions, they might be answered over here. We've got our code of conduct. It's good to review. We've got more information about your final pitch, the judging criteria, just general hackathon tools, suggested data sets, project seed ideas, just, yeah, good things to check out if you need inspiration or you're looking for different tools. And of course, we've got the help desk. So we've got our organizers listed here. Please feel free to reach out to any one of us on Slack with questions. We're happy to help. And we also, of course, have to shout out our sponsors. Without them, this would not all be possible. So shout out to everyone here. And also shout out to our in-person site. So if you are participating virtually, but you see your city up here, you can go on Slack and search for site dash whatever the location is in channels to connect with other people in your city. Yeah, so that's our Miro overview. If you have any questions, yeah, reach out on Slack. We're all here. Just make sure you're in the Slack group. Make sure you have the Zoom link handy. Great. I'll stop sharing my screen. From here, I'll go ahead and hand it off to Calvin for opening remarks. But so for those of you who don't know who Calvin is, so Calvin Lee is the founder of FUM Inc. He's spent years working in the tech world, developing software solutions with companies like Google, Airbnb, Uber, and Meta. And he's now working to develop digital assistants for material science applications. Yeah, so Calvin, take it away.
Yeah, thank you so much for the introduction, KJ. I hope everyone can hear me well and see the presentation that I'm sharing. So once again, welcome everyone to the second annual LLM Hackathon for Applications in Materials and Chemistry. Just wanted to go over a little bit about what are the goals of the hackathon for everyone. And so the goals are to connect domain experts, computer scientists, students, and others to really build that sense of community, provide hands-on learning experiences for everyone involved, build long-term community, and also really just build cool things with potential for impact. And I think we can get a lot done. So a little bit about myself and my background. I think I get this question a lot, like what am I doing in chemistry and / material science space? I personally don't actually have much chemistry and material science space. I did enter undergrad wanting to be a chemical engineer, but due to my clumsiness, I decided that this was not a fruitful profession. My chemistry teacher taught chemistry for 40 years, and I was the only one to ever use the eyewash. So I felt like it was a bad fit in terms of survivability. So then after grad school, I spent about a decade in big tech, working at Google, Uber, Airbnb, and Meta. And the reason I'm attracted to material science and chemistry is that I actually do think that materials informatics is one of the top 3 problems for humanity overall. So I think everyone can agree on AI, and I think this is the only area where I think we've sufficiently invested. The second area is scalable causality. Is like, how do we understand how things impact and cause other things in the world? And because of how complex and rich the world is, we actually really struggle with causality, and something that AI doesn't really touch at all. AI is prediction, correlation, causality is a different matter entirely. And finally, materials informatics, I actually believe is one of the top 3 problems. And despite it being the top 3 problem, I think there's a really big gap in terms of what is the software infrastructure needed versus what's available in order to really scale out and understand materials informatics. To the point of, I know I'm preaching to the choir here, but semiconductors and material advancements and how we sort of evolved through the ages is defined by our materials. I think climate change is fundamentally a materials problem because we struggle to sort of create things without harming the earth. And any scalable climate solution that doesn't require like massive human behavior change is a function of the materials that we have available, such as, composites for wind turbine, battery chemistry solution, even things like, the magnet strength for fusion reactors. And then finally, we are all very excited about the potential for what discovery might entail in terms of being able to discover new compounds and new chemicals in terms of advancing the economy and also our lives. So I want to go over a little bit about what we were able to accomplish last year. So we had really great participation. I think we have some order of magnitude more people than the number of people last year. I don't have the exact numbers, but as you can see, we were able to get a big presence in terms of social media and also YouTube. We have a paper published and so far has 39 citations, and I'm sure there'll be more within the coming months. And so there's a great visibility and great outcome from last year, and we're super excited about this year. I just wanted to sort of go over what has happened with LLMs in the past 12 months. There's basically a titanomachy between basically all the large companies that are well capitalized to basically build much better models than we had 12 months ago. And then on top of that, I think we've also developed a better understanding of what are LLMs actually doing, why do they work, and what are some of the known limitations of the technology. So just to go over a bit about what are LLMs, first of all, what are language models generally? So language models are things that sort of generate words in some kind of algorithm and format. And so I just wanted to take a step back and say that the concept of a language model isn't tied to the transformer architecture. And so you can think of humans as a language model. Of course, we're much more advanced than what we have. But I just wanted to say that we should decouple the concept. So then we have to then ask the question, like, what are generative pre-trained transformers or GPTs capable of? And what are the limitations of the current technology? And so I think a good black box representation of what they're capable of is to think of them as sort of the next word slash token generator. And one of the insights that we have is that words and the way that we leverage language represents really complex ideas, and LLMs have been trained to reflect those complex ideas. So essentially, what are they capable of, right? So you can think about them as pattern matching machines and only pattern matching machines, but also some of the logical limit of what pattern matching machines are capable of. So you have GPT-4 playing chess against Stockfish. Spoilers, GPT-4 loses, but it's able to sort of understand the complex structure of the game and actually still play the game. But when it comes to things that require algorithm and reasoning and recursion, like long multiplications, it's unable to do that because of the pattern matching aspect of it and sort of the entropy related to the multiplication task. I talk a little bit about more in my blog where I sort of explain like why LLMs work. There are ways you can sort of get around the fact that they understand well, but not reason. And two of the really popular techniques are to use agents and to leverage chain of thought. So I also wanted to do a little brief industry overview about companies that are available in the LLMs slash in the chemistry and material science space. It's not all the companies, so I apologize if I missed any notable companies out there. So there's our company, and our goals are to build customizable digital experts and index the world's materials data. So feel free to chat with me if you're curious about what we're building. We have Citrine Catalyst. Citrine has been around as a well-capitalized company in being in development of materials, and also they have recently sort of focusing on building LLMs. And of course, we have to mention Microsoft with their Azure Quantum Elements platform, and they've done a really great work in building a very compelling platform for material science that involve LLM applications and tools. So how might LLMs impact material science and chemistry? We'd love to have you guys show us because nobody has all the answers about what are all the possible applications. And it's a really exciting time to be working on this. LLMs can really revolutionize the way we work with chemistry and material science, and it's extremely exciting. And so we're super happy that you're joining us for the next couple of days, sort of ideating on what's possible. So I understand that teaming has largely been done, but I just want to provide 3 seeds of inspiration. So one thing that people are looking at LLMs for are scalable extraction. So how might LLMs scale data extraction at scale? And so here's a picture of a technical report. And before, it was a very Herculean task to get data from here. And now we have the hope of being able to do structured data extraction and also do qualitative indices. Can LLMs understand intent and unify intent across people? Can LLMs understand what people are looking for and also simplify ontologies so that there's a better chance the data can sort of talk to and work with each other? And finally, the thing that I think a lot of people are excited about is qualitative indexes. So can language models make sense of human observations and sort of unify them in some meaningful way? So if you think about things like that are saying, like, I want something that feels soft to the skin. I'm sure there's a potential quantitative explanation, observation that you can make, like things that you can sort of make up, but most of the really interesting information do exist in human observations and written down in natural language. And so it's really exciting to see if language models can actually help make sense of this information at scale. And that's all I have. Thank you for listening. I'll turn it back over to KJ.
Great, thanks, Calvin. Those are great opening remarks. Our next speaker is Elsa Olivetti. She's a professor at MIT, and her research focuses on improving the environmental and economic sustainability of materials, and she's made foundational contributions to the usage of LLMs and language models in material science applications. So Elsa, oh, there you are. Elsa, I'll turn it over to you.
There we go. Awesome. All right. I trust folks will tell me if things are not behaving as they should. Thank you so much for this. That was a great introduction. Or welcoming words. I was moving things around to make sure I wasn't redundant with what you guys just heard, but I'm really excited about the opportunity to say hello to you all. I think, as we've just heard, there's tremendous opportunity here. And particularly the opportunity of using LLMs to work across flexible modalities of data that we know LLMs and the associated model capabilities can learn rich and dynamic behavior, and that they can operate on discrete systems or continuous systems, symbolic systems that really can describe physics. I think that's the real opportunity we have in pushing the boundary on how they can be used in materials and chemistry. And the kind of fundamental material science, kind of paradigm around that is that we know that hierarchical structures exist in material science. We know those are the scales of that are in length, in time, in modality. And the comments that were just offered about kind of the predictive capability of these models is impressive, but also their ability to generalize and interpret mean that we can really take advantage of this. So I am so excited that this group is here to explore broadly and constantly. My call to action to you all is, play, benchmark, document, keep in close touch, systematically test what you're doing. All of those things are fundamental to making the kind of progress that we need to. And I'll just underscore the point that was made earlier around kind of what the real need is, that we know in climate sustainability in particular, that new technologies are required in every sector to address these challenges. And this pie chart in the middle here that talks about global fossil fuel and industrial emissions, I have these popped out pieces of the pie that are those sectors that we can't decarbonize using existing technologies in long haul transport, in materials production, in distribution losses, and those are fundamentally linked to materials advances. And so, focusing hard on leveraging the most significant model capabilities to really design new materials is fundamental to our ability to move on societal challenges that we need to. But the point that I always think is really critical is that context matters. So we talk about the design of new materials for batteries, for example, but those materials exist as part of supply chain. So what I'm really excited about in the vast rapid capability of LLMs and the ways in which this community is responding to the call to action means that, what if we were designing the battery material? Think about this while you all are hacking away today, with full knowledge of the supply chain that that is part of how it operates. And so that's kind of my call to action to you guys. We know that there's this practical gap between how we want to be designing materials, as shown on the left, the sort of current paradigm of having a concept, doing synthesis and device characterization. And we know we want to be moving towards these closed loop inverse design based structures, and having the idea to do generalizability, generating data of sufficient and quantity and quality, and the ability to measure success is critical. And so that's part of what I think we really need to be moving quickly on. And given the opportunity that the model capabilities offer, I think it's possible to do there. So there was the introduction provided this awesome grounding in the role of well, I guess the idea of decoupling language from transformer models. I want to kind of push in hard on the opportunity of transformer models, really kind of overly in the weeds around the roles of the attention architecture, and why that's so fundamental in the revolution that it offers in terms of materials. So this schematic is taken from a review paper that Marcus Buehler has put together, focused on deep language learning models for interpretive and predictive material science. And what we know is that what the attention mechanism lets us do is offer this opportunity for interpretability, because we can look, which gives us strong generalization capabilities, to start to try to learn truths of physical systems and solve specific tasks, leveraging foundational models, but then looking downstream in that problem space. And so this very, this ability to leverage across modalities, but in a comprehensive black box way, but then being able to know what it is that the models are paying attention to at every step to make this prediction, means that we can make increasingly efficient use of this in-context information and get better performance across different benchmarks. So I'm really excited about the capabilities that this offers. And if we start to dig into this more, and why I think kind of the benchmarking and documenting are so critical to what you all are doing today, and what you all will continue to do in your work, is what if we start to think about that, the mining the transformer architecture itself to yield even broader physical insights, and start to think about differential systems. So these are not my ideas. These are ideas leveraged from this paper. One thing that we know that we're at the cutting edge of this field is that all these really rich papers that are making modeling contributions or making experimental contributions also do a really beautiful job of teaching us, right? The sort of pedagogy of what these models are and what they're doing is a fundamental part of that. And so I think there's the other thing that I'm really excited about, and why I think we're at this sort of tipping point in terms of using these models and these capabilities, is work like what was done at Princeton in LLM prop, and folks are probably familiar with this, is not only are we becoming more versatile with the large language models themselves, we're also incorporating the kinds of tools that the community has been using to date, graph neural networks, using to learn the contextual representation, as we've done in the past 5 or 6 years, but then leveraging LLMs to get around some of the challenges with graph neural networks, in this sort of challenge around periodicity that is often talked about in the neural network space, and the ability to make use of text in order to point to that, and incorporate critical atomic and molecular information embedded within that. And so that that's one kind of measure of success I see in the field advancing. And then the other thing I'll point out in terms of kind of the cutting edge of where I think things are, why I really think that there's a moment here, and I'm so excited about the extent of this community, is this sort of match between the workflows and the ways that folks are stacking LLMs together with neural networks, et cetera. As is sort of shown at a high level in this co-scientist example, the local example for the Chicago crowd, this idea of matching the workflows and how we're scraping data, how we're using LLMs, how we're documenting things in the experiment, there's a lot of analogy to that in how we think about autonomous labs, autonomous experimental work. And so the idea to think about this, it sort of puts another edge on the digital twin framework, which I really like, and makes it clear to us how to leverage domain experts to help frame the problem, to help match those workflows. I'm showing a lab on the right out of Berkeley, similarly leveraging LLM capabilities and the ability to mine text, but linking that with experimental paradigms going forward. So just by way of kind of wrapping up, I was doing a little kind of retrospective as I was putting these thoughts together, and I found this table that I had made that I had pulled from Bryce Meredith in the early 2010s, of citrine fame, where we were kind of, as material scientists, coming to understand what's different between our space in machine learning and traditional applications of AI, and the material space. And these are very familiar terms to us: data volume, data representation, predictive, how to establish domain knowledge, how to model uncertainty and interpretability. So these are problems that, that I think we all now cite as what we need to be doing in terms of leveraging LLM's capabilities. And so the fact that we're able to understand how we're making progress on these challenges that Dr. Meredith pointed out to us in the 2010s, I think is a measure of our ability to start to move on the kinds of use cases that were mentioned: constructing large data sets, structure and property predictions, and materials design. So the group that I get the honor of working with at MIT, we've been wrestling natural language processing for a long time, since pre-LLM world, and I think that the lessons that we've learned there across the set of cases that I'm showing have been really a measure of balancing how do we do generalized transferable approaches to extracting structured information from unstructured free-flowing language, and how do we tailor that for specific examples. So I'm showing alloy design, looking at scalability in sodium-ion batteries and low CO2 cement. Some of my group members are going to hack with you all today, and I think it's great that they're taking part of that. And so I think, we can continue to learn from and reflect as a community, what these opportunities are. As was said in the introduction, my motivation in this space is a lot about sustainability. And so I can't let my slot go away to presenting to you all today with, as we're talking about computing for innovation and sustainability, we have to ground that in what it means to be sustainably computing. And the schematic I'm showing here is from a white paper that we just published at MIT on the climate and sustainability implications of generative AI, led by postdoc Noman Bashir, who's shown here. And we have to be thinking about the compute-related impacts, the supply chain impacts, the operational impacts of the models that we're developing, in addition to the much broader system-level implications of these models. And these models show up on the radar. They are on the order of aviation in terms of their climate impact. And Emma Struble at CMU and folks that she's worked with at Hugging Face have do great work among many others to try to quantify what is the cost of AI deployment, and how does that vary by the task that you're performing, the amount of inference, the amount of local compute. And so I think this is a really important thing for you all to be thinking of as you're hacking away. What is the benefit of what I'm doing? How do I start to measure the benefit of what I'm doing at the local level, at the system level, at the cross equity concerns? And so I really encourage you all, as we're trying to make the next best material to be decarbonizing, how do we think about doing that in a way that is sensitive to the broader climate and sustainability implications of computing itself? So I'm eager to learn from you all how you start to think about that point as well. So with that, I'll end and say thank you so much for your participation today. I'm really excited to see what you all turn up.
Great, thanks, Elsa. I really like that emphasis on sustainable computation. That was awesome. All right, our next speaker is Marwan Segler. So they're principal researcher at Microsoft Research AI for Science, and he works at the interface of machine learning, reinforcement learning, chemistry, and drug discovery.
All right, can you probably hear me? I'm at in Vienna at iClear. So, and can you probably see my screen? Hopefully.
Yep, that's great.
But yeah, I'm going to walk you through kind of how we can go from, let's say, more specialized generative AI models to general generative AI models and language models in chemistry. First of all, acknowledgements is a huge team effort behind this work, and I'm also going to talk about not just work from our team, but also from other work I find really cool. First of all, why molecules and materials? It's really a matter of life. Small molecules and materials change the way we live in the forms of agrochemicals, materials, and hopefully prevent us from dying in the form of drugs. And we need to be able to accelerate the development of new materials and molecules, and also not just accelerate, but also increase our understanding of chemistry and biology along the way. But I think the way how we use computers in chemistry still today is relatively limited. I mean, we can run sophisticated theory and simulations, and that's great. And we use computers to kind of store and look up data. But I think we need to be doing more, and this is great to see. This is now slowly emerging direction again. So what can AI do for us and help? And it's not that AI hasn't been studying chemistry for a long time. So back to the 80s and 90s, people studied neural networks for chemical problems, but it was always this paradigm of you need to somehow transform your chemical data in some feature representation or descriptor representation, and then you can predict a number or a class labels. You can do a regression classification. That was pretty much it until the advent of modern deep learning, and large language models are obviously a subset of modern deep learning, modern deep neural networks, which essentially can process any kind of raw output and produce basically any kind of output, not just numbers or class labels, but any kinds of structures, and can also be used for decision making in a reinforcement learning context. And what's extremely exciting now with large language models is that we finally not just can process raw chemical structures or materials structures, but also natural language. And that's extremely exciting because that was very hard until recently. And usually molecular materials discovery is iterative, going in these analyze, design, make, test cycles. And I show you a few examples where I think generative AI can map onto these steps, which is essentially all of them, in the form of generative design, but also property prediction synthesis, and then learning to analyze data as well, with a new addition now that with LLMs that can reason, we can also start to orchestrate all of these steps. Generally, if we want to find or design new molecules, we actually not just care about so much about the structures themselves, but rather we care about the properties that these structures have. And we can, when we want to find then new structures, new molecules that have these properties, we can either do virtual screening, so we prepare a library of materials or molecules, score all of them with machine learning models or simulations, and then pick the best ones, and that can become very expensive, especially if we don't kind of want to score those molecules in computationally, but we may score the molecules by actually synthesizing them in the lab. And the kind of algorithmic principle to do that is de novo design or inverse design or generative design, where we have some optimization algorithm that can take previous simulations or experiments to find and suggest better structures. And a key component for this is first being able to generate reasonable structures, be it molecules or materials. We want structures like the one on the left, which are reasonable and likely synthesizable. And if we show our chemistry colleagues structures like the one on the right, you do that a couple of times and then you have lost your collaborator, because that's clearly nonsensical. And now with LLMs, we have a word of that. It's an hallucinated structure. And one way how specialized generative models have been used in this context is to train, for example, autoregressive models to generate such structures. So we parameterize the probability of the next, let's say, symbol, next atom in our representation of choice. So SMILES is very nice because it's a sequential representations of molecules, and then can train an autoregressive model to estimate the probability of our molecular structures. We can pre-train such models on very large data sets. And what at the time was a quite surprising finding, you can use that to sample new structures which match the distribution of your training set, but you can generate new structures within the chemical space of what you trained on. That's pretty nice for drug-like structure generation, for example. And now you can use your pre-trained model to either fine-tune those models towards the chemical space that you like to generate within the chemical space of your interest, or you can do reinforcement learning to steer your model with some kind of scoring function in the direction that you want, and generate structures which satisfy your desired properties. There are now numerous examples in the literature of using these chemical language models in practice in a prospective way. Also tested in the lab from various groups here. A lot of work from Francesca Grisoni's group, for example. And also in our collaboration with Novartis, which I unfortunately can't into too much detail about, we're using these models. We have a very large number of molecules now synthesized in active ongoing medicinal chemistry campaigns in portfolio projects in the real world setting in pharma. Where with the help of specialized generative models trained on molecular structures, we can accelerate finding molecules that have exactly the right properties that the chemists need at the time of the stage of their projects. And here I give you a few examples what I find super interesting, which now starts to become possible with large language models. And again, this is huge body of work now coming, and I'm talking about some of the work that we've been on at Microsoft, but also about other work which I really like, which you hopefully have all seen. So first, we have done this small study at Microsoft, which has about 200 pages. So if you have some time at your hands, read this. It took a while to get it approved for reasons that you can imagine, but it's now out on archive since a while. And there we have looked at how LLMs, GPT-4 specifically, performs on various scientific tasks, from electronic structure to drug discovery to materials to various other things. Huge team effort. And the first thing I wanted to show you is condition optimization. So finding appropriate reaction conditions for chemical reactions. So what's above and below the arrow. And usually this is done with Bayesian optimization. Here my colleague Jose tried to see if we can do this with GPT-4. So with an appropriate prompt and system message, can the GPT-4 agent can actually find appropriate reaction conditions. And when comparing this to kind of state-of-the-art Bayesian optimization, we see that actually the GPT-4 model performs quite favorably, maybe not as good as kind of the dedicated Bayes-op algorithm, but it's getting pretty close out of the box, which is super powerful and kind of speaks for this general scientific reasonability. And then I wanted to show you this example about molecule editing, which I think is, is completely mind-blowing because, yeah, just a couple of years, it would be kind of unthinkable that this ever works. But here, I put in some molecule and then asked the GPT-4 model to make some modification. So in the structure, can you replace chlorine with the atom kind of below the periodic chlorine in the periodic table? And we find, yeah, it's completely fine. It knows bromine is below chlorine in the periodic table, so correct substitution. And then I asked, now can you expand kind of this pyrrolidine, this 5-membered ring, into a piperidine 6-membered ring? That's also working fine. Sounds good. But then if I ask, can you use a 3-hydroxypiperidine? It gets the position on the ring wrong, so it produces the 4-hydroxy, not the 3-hydroxy. So I have to ask again, and then it gets it right. And then I can ask for a bioisostable replacement, so replacing the central amide here with a suitable group, and also makes a decent suggestion. So I think it's a super cool indication that yeah, this purely, I mean, doesn't have all the details right, but it's certainly getting there. And with a few iterations of GPT Next models, I think we'll pretty clearly see where this is heading. Kind of the TLDR of our paper is, with GPT-4 for scientific discovery tasks, we get some promising new capabilities, but it's in our experience, at least, we don't fully see that it can completely replace specialized algorithms yet. But let's see what happens in the next couple of years. Some other directions I find really interesting is augmenting the language models with tools. So this is the ChemCrow study that was pretty widely known, but I highlight it for you again, which actually got published today. So congrats, yeah, everyone involved here. Super nice paper showing basically that you can couple the language model with various chemistry tools. So various APIs, ability to search, ability to do retrosynthesis, ability to train models to solve quite a few variety of problems, and moving towards kind of automating science. I'm super curious in which direction this will develop. Gabe Gomez's paper was already mentioned, so I skipped this here. For me, some open questions in this whole space are how we generally test the quality of generative systems, because the more complex, let's say, our structured output of these models becomes, the more hard it gets to test, the more harder it gets to compile test sets. For regression classification, it's easy. For structured, sophisticated output, it's hard. So one of the things that we've done in the past for models that produce structured output in the context of chemical synthesis planning is to do A/B testing. So producing different outputs from a model and choosing kind of ground truth outputs from the chemical literature, and then asking experts in a double-blind way, do you prefer A, do you prefer B? And then doing statistics, and then seeing, for example, actually when comparing that the chemists can't distinguish between the output of a good model, and can't distinguish the output of a good model from the ground truth, but can very well distinguish the output of a good model from the output of a bad model. So in a way, a chemical Turing test. And I think for LLMs, we should hopefully see more of that. Open questions for me are many, and I want to give you some thoughts for a hackathon to think about. At least these are the things that I think about. So one is, how do we augment experts rather than replacing them? How do we mitigate risk and dual use? We have kind of chemical weapons in mind potentially, but there's also so much good we can do with these models. How do we best integrate generalist reasoning models and specialist models and representations? And one big one for me is, how do we develop benchmarks when we don't know what's actually in the LLM training data. So we need to assume these LLMs have been trained on everything that's on the internet essentially. And to be able to really make impact and discovery is how do we actually operationalize novelty in scientific discoveries? How can we tell whether a model has actually discovered something meaningful, or is it just kind of a reproduction or maybe trivial extension of something which is already known? Yeah, with it, thanks for your attention and thanks for the invitation to speak, and looking forward for what you all hack together.
Thanks, Marvin. I see there's some questions in the chat, so if you have a minute, it might be good to see if you can respond to those. All right, let's move on to our next speaker. So our next speaker is Michael Craig. He's a senior scientist at Valence Labs, where he researches AI applications in drug discovery, and he holds a PhD in the neuroscience of consciousness. Michael, we can see your screen, but
Hi,
if you're
everyone.
talking,
Just
I
getting
can't.
the
Okay,
just
good.
getting unmuted. Can you hear me now? Sorry about that.
Yes, we can hear you.
Hi, everyone. Can everyone see that the screen looks okay? Yeah,
Yep.
let me know if anything goes wrong. Yeah, thanks very much for the invitation to speak here today. My name is Michael Craig. I'm a senior scientist at Valence Labs. Valence Labs is an independent research organization within Recursion Pharmaceuticals, and we're really focused on more long-term research goals of the organization, all like around industrializing the drug discovery process. And today I want to talk to you about some of our early work using language agents for autonomous workflow orchestration. So really our focus now is kind of an extension of what Marwan just was discussing. Like how do we use these language agents to orchestrate various industrialized workflows within the drug discovery setting. And I'm sure many of you have seen slides like this. So just a description of how complex the drug discovery process is. So it takes 10 plus years to get a drug to market in most cases, over $2 billion. And the actual search space is massive. So you have 10 to the 60 different Lipinski or drug-like molecules. And the schematic here gives you an idea of really, this is a very high level overview of all the different steps involved in drug discovery, everything from identifying an initial protein target to go after, all the way up to clinical trials. And as you get closer to clinical trials, everything gets more and more expensive and higher risk. And what machine learning has done in the past is try to develop various point solutions for different aspects of this process. So things like improving how we represent biomolecules computationally, improvements in structure-based methods. So like things like AlphaFold, DiffDock can help improve how we identify novel targets and design compounds for those targets. Work in synthesizability estimation as well is quite important. So can we actually create the compounds that the models are coming up with, and explainability as well, also particularly important for working with med chems and biologists who want to understand why models are making the decisions that they're making. So with all of this work in developing all these different point solutions for different steps in the process, the question is, why haven't we seen a bigger impact in machine learning in drug discovery? And I think so much of this is just a difficulty in communicating across these two very complex fields. From a medicinal chemist or a biologist perspective, if I give them a model that is 1% better state of the art or on some benchmark they haven't heard of, they're not going to be particularly impressed by it. And when a biologist or a chemist tells you about the incredibly expensive software they're using that uses linear regression on 50 samples that was trained in the 90s, the machine learning scientists won't be particularly impressed either. So we want to figure out how we can bridge the gap between these two fields and try to start merging expertise here and really develop the tech bio industry overall. Here's just an example of all the different kinds of tools that you could build. This is obviously not exhaustive, but there's so many different steps in the process where you could automate the discovery process essentially. And the question is, how do we put all of these together into a single process? And the way we're thinking about it at Recursion and at Valence and in many other labs across the world is using autonomous AI agents that can orchestrate these tools so that they facilitate the discovery of either novel targets, novel compounds, and can do so continuously and only with like minimal human intervention. And at Valence, we've come up with this product called Low. So Low is an LLM orchestrated workflow engine. It's essentially a way to directly interface with different aspects of the Recursion operating system. So the example here, it's just identifying a set of targets associated with non-small cell lung cancer, returning those targets from the literature, and it's able to give you an insight into what targets are available and give you additional information on them. There's also additional steps I'll show in examples below too. Really what we're trying to do is build out these cognitive architectures is how we're thinking about them. So there's a great work from Princeton, the Koala paper, which I can post in the chat too, where they kind of define cognitive architectures from the perspective of like how do we incorporate large language models into these systems. And from how we think about them is that a cognitive architecture is an agent that has both context for the task that it's working on, the ability to reason about the requests from the user, and also implement that logic in various tools that an LLM itself would not be able to access directly. So in our case, this could be different things like memory storage, tools for prioritizing targets, molecular design, synthesis planning, all sorts of things that go all down the list of tools that a medicinal chemist would use to prioritize compounds and progress compounds down a pipeline. And eventually, we'd like to get to a point where it's as little human intervention as possible in these systems, so that agents can continuously work on within Recursion on the different kind of biological maps that Recursion is building, and also in different partners as well, the data that they're generating. In a little more detail on how orchestration actually works. So users can input questions or requests like design a new compound that has the same scaffold as gefitinib and afatinib, but has better CNS penetration. This prompt will go to an orchestrator, which is a large language model plus a system prompt that defines the system's goal, and then a large set of tools that the system has access to. We use chain of thought in this case to put together the plan for how the agent will execute the order in which the tools are called and what it does with the inputs and outputs of each of those tools. And it can go through a process like my thought is I need to retrieve the structure of these two compounds. I need to take that structure and put it through SAR analysis, so understand why that particular structure is of interest. Using different, and now I need to take that structure and expand that set of compounds to create a new chemical series. And then I need to prioritize that chemical series to get just the top compounds from it. And it goes through this process and eventually reaches a terminal state. And once it gets to that point, it's achieved the goal it's trying to achieve and returns the results to the user. Some more examples of kind of, I thought actually Marwan's examples are really interesting of how you can use GPT-4 directly, and we do use GPT-4 a lot for just just raw GPT-4 for the actual processing of a lot of information. But without the additional tooling, you do lose some additional context. Like the example here is in GPT-4, you can ask, give me the top 10 known drugs for EGFR inhibition, and it can give you a good list of that, but it won't give you additional information like all the different kinds of information you can extract from the literature essentially, and it presented in a structured way. It's kind of a small example, but something that just a difference between these two kinds of systems. Other examples can be looking at osimertinib in this case is a drug for EGFR. You can get a bunch of information about osimertinib in some kind of structured form, but it's not going to be able to explore the chemical neighborhood around osimertinib using, in this case, a variational autoencoder. So for Low, it's able to call a tool that it knows is able to explore the chemical space around the starting point compound and return certain compounds that could be of interest to the user as well. In the interest of time, we'll go through all of these, but just to say that we have issues with hallucinations oftentimes as well. So you can ask GPT-4 to do something in case ChatGPT And it can produce a very interesting solution, but in this case, the actual smile string it generated is not osimertinib. So it can use this, but it's hallucinated the wrong structure in this case. And you can see just the example of how it's expanded around the wrong set, the wrong scaffold, essentially. Some more kind of in-depth example of how low can be used to orchestrate processes. I'll speed this up a little bit too. So in this case, this is the kind of extension of the prompt from above. So what this is doing now is taking an input from the user, which is identifying the, say, top, finding a list of drug targets associated with non-small cell lung cancer. We can return all these results from the literature, in this case, in this form of a bar plot, and you can look at all the different kind of like dimensions that the system is thinking about the data. Further down, this is taking the output of that step and inputting it into a recursion tool. So what this is doing is identifying within the in one of the recursion maps other proteins that have some correlation with the input compounds. And then from there, it's able to use another tool called Matchmaker to take those novel targets that it just identified and identify a novel set of compounds associated with those targets. So you're able to go from an initial question of find me targets associated with non-small cell lung cancer all the way to a novel chemical starting point for a different target that's not from the literature, all in a very short amount of time. And we also have checking mechanisms along the way to just ensure that where the system is not hallucinating. So that's a super interesting area of research as well. I think that would be something that the hackathon could be a really interesting space to explore. And yeah, additional tools down here for generative design and predictive modeling as well. So you're able to take those initial starting point compounds, expand the chemical space around them, and then use predictive ADMET models to help prioritize those compounds further, and eventually also make an order for those compounds and design experiments for them to run within the recursion operating system. The way we want to extend this work as well is to incorporate one additional tooling and also memory modules that are able to keep track of previously run workflows and different information that the system has extracted from the literature, extracted from its own actions within the operating system as well, and kind of give it the ability to think further ahead and think further back in time as well about like what is its context for executing a particular prompt at a certain time. And while language is very powerful, it's probably not enough to capture the complexity of biology. In this case, this is looking at EGFR inhibitor resistance. So this is a very complex biological process, something that occurs after first-line treatments in non-small cell lung cancer in this case. So what we want to do is continue expanding the works to incorporate multimodality as well. So eventually what we'd like to get to a point to be able to do is say, here we have a chemical starting point that we know is a strong inhibitor of a particular target that can serve as a treatment to this particular resistance pathway. However, we know that it's ineffective in patients that have a particular secondary mutation in the binding pocket of target X. Given the observation in the binding dynamics that you see with this new compound and target X, can you suggest additional sets of compounds that could overcome this resistance? So in order to achieve this kind of goal, you need to incorporate multiple modalities, both biological, chemical, and all sorts of kind of more specific modalities that are kind of housed within those fields in order to execute prompts like this. And eventually we want to also be able to get to a point where we can run these systems autonomously so that they can generate their own biological hypotheses, design their own experiments, learn from those experiments, and continue doing so 24 hours a day. So yeah, thanks very much for your time. Happy to take any questions you have.
Great, thanks, Michael. I don't see any questions in the chat, but if you have questions for Michael, you can always find him on Slack or put things in the chat as we keep going. But yeah, thank you. Our next speaker is John Reifschneider. He's a professor at Duke University, where he is the director of the Artificial Intelligence Master of Engineering program. He serves as a director of the Duke Center for Research and Engineering of AI Technology in Education, which is a center that explores the way that AI can improve teaching and learning at Duke and beyond.
Great, thank you for the introduction. Hello, everybody. Great to see so many folks on the Zoom call here and so many participants in the hackathon. I'm gonna share my screen here. I've got a couple of slides I thought we'd run through. So, yeah, a quick introduction. I am the director of our AI Masters of Engineering program here at Duke. I run a small applied research lab looking at innovative ways that large language models can be used in the field of education to improve teaching and learning. I also am the faculty advisor for our Generative AI Hackathon here at Duke. So we held this past year for the first time ever, an AI-focused hackathon event. Very similar to this one. It was held on campus over the course of a long weekend, so Friday afternoon through Sunday. We had a great turnout, a couple hundred students from Duke and elsewhere around the region, building some amazing things in 5 different tracks. And so part of what I want to do today is share some of the lessons we learned from that with you all to give you kind of a jump start and learning from the successes or failures of others in similar types of events. So first thing I want to say is kudos to everybody for joining this event today. I really, even though I teach sort of a foundational AI master's program and classes in sort of the technology of AI, I really see AI as certainly a field of research, but more importantly, a tool in the toolbox of people in really every domain that they may or may not want to use to solve problems. And so I think that people like yourselves are the most powerful users of AI technology because you all are the ones that are deep in your specific domain area of interest. And so you're the ones that really understand the problems to solve there. And you know, through participating in experiences like what you're doing today, you'll add a new tool to your toolbox of possible ways to solve those problems. And so AI can be a very powerful tool, but it's really I see it more as a means to an end, not an end itself. And that's really it's actually a common mistake I see a lot of companies making today, chasing kind of AI because it's the hot thing and they feel like they need to do it and everybody else is doing it and they've got to have some AI thing. You know, and it's really a pretty poor strategy, you know, when you frame it as AI really being more of a tool to solve problems rather than a solution in itself. So that's the first thing and probably the most important thing that I wanted to say to you all today. So I think it's great that you're taking the time out of your schedules to learn about how to build with large language models. So a couple of quick slides, things I wanted to highlight. When you think about building with large language models, there's kind of 2 sort of primary ways to approach it. One is just, you know, take the thing out of the box, you know, GPT-4, Claude, whatever, open source, pick your, you know, Llama 3, whatever, and just use it and apply it to solve some problem. The second is to take that thing and adapt it to your specific domain or your specific problem. And so let's talk about what each of those means briefly. So out of the box is you know, up to today, it really has been probably the most common way that folks have used these models, right? Whether you're hosting your own open source model or whether you're choosing to use an API, doesn't matter. But you're taking a model that somebody else built and trained, and you're applying it to some specific use case, right? So typically in this kind of an application, a user is bringing the data, right? So rather than kind of supplying the data that it's using, the user him or herself is bringing the data with them. And you're typically applying this to sort of one of a number of more standardized tasks. Maybe you're summarizing, you know, scholarly articles, you're asking it to synthesize, you know, different papers, to give feedback, to work as a writing assistant, to give you feedback on drafts of something you're writing, or review a grant proposal, or whatever the case is, right? So your user is the one supplying the data for it to work on, and you're sort of picking one of these different tasks that it's fairly capable at doing. That's pretty straightforward. Where I think it's more interesting is in the area of domain adaptation. So how do you take this powerful tool that is nicely available through an API or to download and use, and how do you customize it for a use case in a specific domain, right? And there are a few different ways to do this. So a very popular one today is what's called retrieval augmented generation, or RAG, where you're allowing users to provide some instruction or ask some question, and instead of just giving that question or instruction to the model and asking for a response back, you're also providing the model with some domain-specific information to be able to answer that question or fulfill that instruction. And so in this kind of a use case, you're actually providing kind of an external data store, external set of data to the model to use when it chooses to do so, to assist your user. This is a really powerful strategy. It works very well for helping the model better react to instructions or questions in domains it's not as familiar with, very niche domains where it maybe hasn't seen a lot of training data in that area. Adapting to kind of current events. LLMs out of the box have sort of a time limit on currency, where you have kind of proprietary sets of data, maybe your company that has sort of product specs or other things, technical papers written about your products or so on, and you want the model to be able to access that information. So this is a very common use case for companies that are working with large language models. And then the second option is fine-tuning the model. So taking that base model that you've gotten, that somebody else has done the pre-training on, and doing some further training of that model for a very specific use case. And this is typically used not so much to kind of add domain information to the model or give the model sort of expertise in a certain domain area, but more to give it expertise in performing a specific type of a skill. So if you want to, so what would an example of this be? Maybe you wanted to read kind of, you're a pharma company and you wanted to review kind of patient emails and sort of extract commonly occurring symptoms related to different drugs that patients have taken, for example. That may be an area where you fine-tuning would provide a great benefit. So any skill that you feel that may have sort of not been a common occurrence in the training data set. So if you're asking a model to do something, it's seen or it's done a lot in its training. So answer questions, for example, summarize documents, provide feedback. Those are very common things that the model is used to doing from its training. It's very capable of doing. It's probably had some fine-tuning on those types of things already. If you're asking it to do something else that maybe it hasn't had a lot of experience with during the course of its training, that could be a great use case to do some fine-tuning, to provide your own data set of inputs and desired outputs, and do some customization of the model to be able to do that. A lot of people tend to mix these two things, RAG and fine-tuning, and they think, oh, if I want the model to kind of understand my domain or sort of have expertise from my, this collection of documents I have about my specific area, I need to fine-tune the model on that. And that's actually, you certainly can do that, but that's maybe not the optimal approach. A better strategy often is for that type of a use cases to try a retrieval augmented generation approach to it before you get into any fine-tuning, because fine-tuning does, it's more complex, it can be more costly. It's not necessarily easy to do it well, and then you have to continue doing it every time you sort of update your collection of data. So there are some downsides to fine-tuning that I think make it probably not the first place you want to jump to when you're thinking about customization for a specific use case. Okay, quick view at retrieval augmented generation, and I'm not sure how much you've talked about this in some of the other talks already, but briefly, the idea here is that you take the model, which itself is generally excels at generating text, but may not be knowledgeable, or at least not enough about a specific domain area. And you hook it up to an external data store of documents related to that area or that specific problem. So the way you do this is you gather a set collection of documents, you create what's called, or you chunk those documents up into sort of small chunks by paragraph or by a set number of words per each chunk. You take each of the chunks and create an embedding, which is basically just a large vector representation of that chunk. It uses a large language model to create this vector representation, which attempts to capture kind of the semantic meaning of what that chunk is talking about. And you store all these vectors in a typically a vector database. When a user then queries your system, asks a question, provides an instruction, it uses that embedding model to create an embedding of your user's query, and it compares the embedding of the query with the embeddings of all of the chunked up documents you have in your vector store, finds the most relevant chunks of text, passes that to the large language model, and then has a prompt that says something like, here's a question from a user, here's some relevant context to help answer that question, use this context to formulate an answer back to that user. And so this is the whole idea behind RAG. To highlight a couple of the learnings from our Duke Generative AI Hackathon that we held in the fall. So first of all, the most important part of all of this is finding a good problem to solve. And this sounds really simple to say, and it's actually hard to do in practice, that we found, probably particularly for students who maybe aren't used to doing this. The way to find a good problem is there's sort of, to solve in this type of event, there's kind of two aspects of it, right? One is identifying a pain point for a user. So where in the user's workflow do you find that they have a particular pain point, something that is very time consuming, something that's difficult to do, something that you think you can maybe help them do better or more efficiently. And then secondly, is a large language model a good fit as part of a solution to that pain point? There's tons of pain points for which you absolutely don't need to use a large language model. Large language models bring some unique capabilities and strengths to bear in solving problems, but ideally the problem you want to solve is sort of the intersection of where you see a clear pain point for a user and where large language models can provide some benefit in terms of being helping as part of the solution to it. Secondly, a lot of people tend to sort of think that the model is kind of the unique thing and the special sauce, that they're kind of going to apply to solve, some problem. And it's typically actually not true. These models are over time becoming more commoditized. There's a lot of great options out there. Every day there's more. Usually the uniqueness in a solution or an application that's successful is achieved through the data, not so much through the model itself. So I think a stronger focus on what unique set of data can I use to help solve this problem, whether you find that somewhere, whether you already have that from your research or from somewhere else, or whether you have to go generate that or get help from your users to generate that. Data is where you usually can create the most differentiation and uniqueness, not so much the model itself. Number three, so when you're in an event like this, in my mind, the practical thing to do is to start by using APIs of either open source or proprietary commercial models. Some students kind of go down this path of I definitely want to do open source and I definitely want to host my own model, and that's great, and that might be the right long-term decision to make and the right long-term vision. But when you're getting started, if you go down that route immediately, you can easily find that you're sucking up an entire day just trying to kind of get your model hosted and working and accessible to you. And it's really not a good use of time. So I always advise start with an API. You can save yourself hours of time. It's very simple to use. Work with an API at first. Number four, before you even get to kind of using the RAG technique we just talked about or fine tuning, start with prompt engineering. Do few shot learning, give it examples of the inputs and desired outputs that you want. Try to do some engineering of your prompt, run experiments. try to optimize your prompting to see what kind of results you get before you jump into RAG or fine tuning, because those are things that take up a fair amount of time and a fair amount of work. And number 5, make sure you give sufficient thought to the user experience with this whole thing and what you want that to be. A lot of people think that's kind of secondary, and I just tend to focus on kind of the model aspect of it. But what we've found, ultimately really makes or breaks the success of an application and whether people are actually going to use it often relates more to the experience they have in using it and less to sort of the modeling itself. So think very carefully about what your desired user experience is, how the user should interact with the model, how much transparency the model should give the user, how much input and direction the user should be giving the model in terms of how it's behaving, how much interactivity you want between the model and the user. All these things are things to think really carefully about. So I think I'll stop there. I know we're at time, so let me pause there and happy to take any questions.
It sounds like there might not be any questions, or people are really thinking on it, and maybe I'll post some questions in the chat or in Slack. Oh, actually, question just popped up.
Yeah, are there any metrics for user experience? Yeah, so yes, I'm not a user experience. I'm not a user experience expert. I have my share of experience with it. I used to build commercial products before I joined the faculty here at Duke. And honestly, from my time in industry building commercial products that people use, the number one metric is what the top two. Number one, are people using it or not? That's a very easy way to tell, is your user experience good or not? Are people using it not only one time, but are they coming back to use it again? That's really the best way to tell. And then if you hit that, and the answer to that is yes, the second metric is, will people pay to use it? Because these things cost money. And ultimately, someday you're going to need a business model that is financially supportive, covers the cost of using it. So, do people find enough value in it that they're paying money to use it? That's kind of the ultimate measure of user experience or usability, is will people come back to use it again and again. Everything else is kind of secondary to that and sort of steps along that, but that's really the best thing that you want to measure. Give it to 50 people, get them to try it once, see if they come back and use it again.
Great. Thank you, John. Thank you to all the speakers. Thank you, KJ. We are basically right on time. If any of the speakers are still around and people have questions, we could ask a couple questions. After this, we're going to move into a teaming session. So if you haven't found a team yet, or you're still trying to come up with an idea, we'll have a session that will continue in the same room. But that's optional. If you already have a team, you can start working on your project. But before we go into that, why don't we just ask if anybody has a couple of questions for any of the speakers. If you want to unmute, go ahead. And in this time, I will stop the live stream and stop the recording.